Good morning, everyone, and welcome back to the MST CET crash course session. So, I'm Professor Omkar Salvi, Assistant Professor in the Mechanical Engineering Department of SSPM'S College of Engineering. Today, I'm going to teach the chapter 1 of physics, which is the rotational dynamics. So, before we start directly with the objective question, you will see the basic concepts. So, this is the overall content of the chapter 1. So first we have the circular motion. So concept of circular motion, then uniform and non-uniform circular motion. After that, we are going to learn the centripetal and centrifugal force. Then application of uniform circular motion. So in the application, the first is vehicle moving on the horizontal circular track. So we will calculate the maximum safe speed without skidding. Second is well of death. So minimum speed of the rider on the wall without falling down. Third application is vehicle on the bank road. So we will find out the equation for angle of banking, safe speed, and the speed limit. And the fourth application, it is the conical pendulum. Next, we have vertical circular motion. So we will find out the equation to maintain the vertical circular motion. So that is the equation for velocity at various point. Then next we have moment of inertia for the regular shapes. And last we have angular momentum or the moment of linear momentum. So this is the content of the chapter 1. So let us see in detail. So first concept, it is the circular motion. So circular motion means what? A rigid object, it is moving in a circular path around a point. That is, object is revolving about the point. Okay. So circular motion is object perform the circular path around a fixed point. So you can see here. So this is the example of circular motion. Okay. So this object which is tied to the string, it is being revolved around this center point. So what are the characteristics for the circular motion? So first characteristic is circular motion is an accelerated motion. Okay. So this accelerated motion, its acceleration is nothing but the centripetal acceleration. So because of this acceleration, any particle performs the circular motion. And second, it is the periodic motion. Okay. So concept of periodic motion is, in the circular motion, the object passes through the same point again and again after a specific interval of time. Okay. So therefore it is a periodic motion. So graphically we can represent the circular motion like this. So this is the amplitude versus time. So it will follow this sinusoidal graph. Okay. So here y-axis, it is the amplitude or the maximum displacement with respect to the mean point. And this is the angle or the time. So this is theta or the time t. Okay. So these are the characteristic for the circular motion. So let us see the kinematics of the circular motion. So in the kinematics, we are going to calculate the angular velocity, angular acceleration, and the tangential velocity. Okay. So you can see here, the point P performing the circular motion around a circle of radius r. Okay. So as the point P is moving on the circular path, you can see there is a change of angle theta with respect to time. Okay. So in order to calculate the angular velocity omega, if you differentiate this theta with respect to time, then we will get the angular velocity. So omega is equal to d theta upon dt and its unit is radian per second. Okay, so omega, it is the vector quantity. So this is the omega bar, which is a d theta upon dt. Suppose this particle performs circular motion and its velocity is continuously changing, then it will have the angular acceleration. So in order to calculate this angular acceleration, we need to differentiate this angular velocity with respect to time. So alpha is equal to d omega upon dt, and its unit is radian per second square. So angular acceleration, angular velocity, both are vector quantity. So this is the alpha bar. Next is the tangential velocity. Okay, so tangential velocity means what? You can see here this vector. So this is the tangential velocity, or we can call this as a linear velocity. Okay, this velocity v, it is always tangent to this circular path, and it is perpendicular to the radius vector. So you can see in this example, this is the v bar, which is the linear or the tangential velocity. As this velocity is tangent to the circular path, it means it is perpendicular to the radius vector. So this angle is exactly 90 degree. Okay. So tangential velocity we can calculate by using this formula. V is equal to r into omega, and unit is meter per second. Okay. So this r into omega, it will give the magnitude. Okay, and this is the vector equation, which is the v bar is equal to omega bar cross product of r bar. Okay, so the cross product of omega and r, it will give the velocity. That means these three vectors, velocity, angular velocity, and the radius vector, they are mutually perpendicular. Okay, so you can see here the angular velocity vector omega, we can give the direction of this omega by using the right hand thumb rule. Okay, so you can see here this is the direction for the rotation of the particle which is performing the circular motion. Okay, then curl the finger like this, and thumb, it will denote the direction of angular velocity. So let us take the example. Suppose this is the particle P, and it is performing the circular motion, and this is the direction for the circular motion. Okay, so if this is the direction of circular motion, then this vector, it will denote the angular velocity. So this is the omega bar. So this direction of the angular velocity, it is given by this right hand thumb rule. Suppose particle is performing angular velocity in this direction. So as per the thumb rule, curve the finger in the direction of this velocity, and this thumb, it will denote the direction of angular velocity, which is the omega bar. Okay. So by using this thumb rule, we can give the direction of angular velocity and the angular acceleration. Okay. Suppose this velocity, that is a v bar, or this angular velocity, okay, it is changing with respect to time, then it will have the angular acceleration. Okay, so angular acceleration vector is also parallel to the angular velocity. So this is the angular acceleration vector, which is the alpha bar. Okay, now let us see the uniform and non-uniform circular motion. Okay, so uniform circular motion means speed of the particle remains constant during the motion. Okay, so speed is constant and direction of the velocity changes, and the velocity is always tangent to the circular path. So in the circular motion, direction of the linear velocity or the tangential velocity is always changing. Okay, but in the uniform circular motion, its speed will remain constant. Now the acceleration is a radial acceleration in the uniform circular motion or non-uniform circular motion. Okay, and this acceleration, it is given by a bar is equal to minus omega square into r bar. So this is the centripetal acceleration. So this is centripetal acceleration. Okay, which is a is equal to minus omega square into r bar. Acceleration magnitude, is constant for the uniform circular motion, and this acceleration is given by a is equal to omega square into r. So this is the magnitude. As omega, this is equal to v upon r. So we can replace this omega square by v square upon r square into r. So we get the equation for centripetal acceleration is v square upon r, or we can write this equation as v into omega. Okay. So for the acceleration in the uniform circular motion, we have three equations. One is omega square r. Second equation is v square upon r, and third equation is v into omega. Okay. So just you have to remember these two equations. V is equal to v upon r. Sorry, omega is equal to v upon r, and acceleration is omega square r. Now the acceleration is always directed towards the center. So this is the centripetal acceleration. So you can see here in this diagram, this particle P, it performs the circular motion, okay, around the point C. This is the radius vector. So this is the direction of the centripetal acceleration or the radial acceleration, okay. It is always directed towards the center of the circle. Now suppose if t is the time to complete the one revolution in the uniform circular motion, then its angular velocity omega we can give by using this equation. Omega is equal to 2 pi upon t. Or if the frequency is given instead of time period, okay. So time period is the inverse of the frequency. So it is a 1 upon n, or n is equal to 1 upon t, okay. So we can give the equation omega is equal to 2 pi n. So one formula for omega is 2 pi upon t, that is the time period. In terms of frequency, this is 2 pi into n, okay. And where the frequency, it is the inverse of time period, or time period is the inverse of the frequency. Sometimes frequency, instead of hertz, it is represented as a RPS. So meaning is same. This is the revolutions per second, or the oscillations per second. So oscillations per second is nothing but the hertz. Okay. So for example, if the frequency is given as a 10 hertz, okay. So 10 hertz means what? The particle or that object, it performs 10 oscillations per second or per unit time. Okay. So this is the meaning of 10 hertz frequency. Okay. So second type in the circular motion is non-uniform circular motion. Okay. So non-uniform circular motion means angular velocity, that is the omega, is changing with respect to time in the circular motion. Okay. Centripetal acceleration AR is not constant. So as omega is changing, then acceleration will also change, because the formula for acceleration is, this is omega square into r. So as omega is varying, acceleration will also vary. Okay. Angular acceleration alpha, that is alpha bar, is also changing. Okay. So this angular acceleration, it depends on alpha is equal to, or alpha bar is equal to, this is d omega upon dt, or this is second derivative, that is a d square theta upon dt square. So in the non-uniform circular motion, omega is changing with respect to time, and therefore the acceleration is also changing. Okay. So here you can see the difference in the vectors for increasing speed motion and decreasing speed motion. Both are non-uniform circular motion. So if the omega is increasing, then this angular acceleration vector will be exactly parallel with the angular acceleration vector, sorry, with the angular velocity vector. Okay. And if the speed is decreasing, then this angular acceleration vector is exactly opposite to the angular velocity vector. Okay. So here alpha is positive and here alpha is negative. That means speed is decreasing. Okay, so this is about the non-uniform circular motion. So omega is changing, centripetal acceleration is changing, and the angular acceleration is also changing. Now these are the kinematic equations for the rectilinear motion. So you must have studied these equations in the 11th. First is the V is equal to U plus AT. V square is equal to U square plus 2AS, and S is equal to UT plus half AT square. Okay. So similar to the rectilinear motion, we can write the kinematic equation for the circular motion. Okay. So just we need to use the equivalent terms. So here V is the final velocity, U is the initial velocity. Okay. So we can use omega 2 as a final velocity and omega 1 as the initial velocity. Next, A is the acceleration in the rectilinear motion. We will use alpha as an angular acceleration in the circular motion. S is the displacement in the rectilinear motion. We will use theta as a displacement, that is angular displacement, or angle turned by the particle. T will remain same. T is the time. Okay, now write this equation. So first equation, V is the final velocity. So we can write the omega 2 as a final velocity, which is equal to omega 1 initial velocity plus A is the linear acceleration. So alpha is the angular acceleration, alpha into T. Okay. So omega 2 is equal to omega 1 plus alpha into T. Second equation is V square. So omega 2 square equal to U square. So it is the omega 1 square plus 2 into alpha into theta. Okay. So this is the second equation in the circular motion. And third equation is for the displacement. So it is a theta instead of S. This is equal to ut. So it is the omega 1 into T plus half into alpha into T square. Okay. So similar to the rectilinear motion, we can write these three equations for the circular motion. Okay. So these are the kinematic equation for the circular motion. So we can use this equation if A1 value is given and we have to calculate the other value. Okay. Next is the dynamics of the circular motion. Okay. So meaning of dynamics is we need to consider the force causing the motion along with that motion, that is the kinematic parameters. So in the dynamics, we are going to deal with the forces which causes the motion. So first we have the centripetal force, which is responsible for the circular motion. So in circular motion, resultant of all real forces is directed towards the center, and this force or resultant force is called as a centripetal force. So centripetal force is the real force. Okay. So we have the basic equation by using Newton's second law. F is equal to mass into acceleration. Okay. So we know the acceleration in the circular motion. It is the centripetal acceleration, which is a minus omega square r. So we can write the equation for force, which is equal to F is equal to minus mr into omega square. So this is the formula for centripetal force. So just magnitude we can write as a mr omega square, or we can write mv square upon r. So if you replace omega by v upon r, then we will write mv square upon r, or mv into omega. Okay, so here we get three equations for the centripetal force. One is the mr omega square, second is mv square upon r, and third equation is mv into omega. Okay, then second is the centrifugal force. So centrifugal force is the non-real or the pseudo force. It arises due to the centripetal acceleration of the frame of reference. Okay, at the uniform speed, in this is the example for the centripetal and the centrifugal force. In merry-go-round, centrifugal force equals to the centripetal force at the uniform speed. Okay, so we get the equation centrifugal force, which is equal to the net pseudo force, and at the equilibrium, all real forces, that is the summation of all real forces, it is equal to minus mr omega square. Or we can write this equation as summation of all the real forces. So all real forces is nothing but the centripetal force plus mr omega square. It must be equal to 0. So this is the condition for the equilibrium. Okay, so we can experience this condition when the merry-go-round is moving with the uniform speed. Okay, at the uniform speed in the merry-go-round, centrifugal force, it is equal to the centripetal force. Okay, next we will see the applications of the uniform circular motion. So the first application, we have vehicle along horizontal circular track. You can see here, this is the center of the circular track. Suppose this is the circular track and it is having the radius r, and this is the vehicle. So it is moving with the velocity v. This is the linear speed or the tangential speed. Okay, so for the equilibrium, the weight of the vehicle, it is balanced by the normal reaction which is offered by the road or the ground. So mg, this is equal to n. Then static friction, fs. So this is the static friction. So it will stop this vehicle from the skidding. So fs is equal to mr into omega square. Okay, which is equal to mv square upon r. So if you take the ratio fs upon n, that is static friction upon the normal reaction, which is equal to r omega square upon g, and it is equal to v square upon rg. So for the maximum speed or the safe speed, at maximum speed of the vehicle on the curved road, the fs, that is the static friction, it will reach to its limiting value. Okay, so this limiting value is nothing but the fmax value. So replace this fs, that is the static friction, by the maximum value or the limiting value. So it is a fmax upon n, which is equal to vmax square. So it is the maximum velocity upon rg. Okay, now from the equation of the static friction, we have limiting friction fmax. This is equal to coefficient of static friction into normal reaction. Okay, so we can replace this fmax upon n as a static friction. So this is the coefficient of static friction. Okay, and from this equation, you will get the equation for maximum velocity on the circular track, which is equal to square root mu s into rg. Okay, so by using this relation, we can find out the maximum speed of the vehicle on the horizontal circular track. So you need to remember this equation. There can be question on this equation to calculate the maximum speed. of the vehicle on the horizontal circular track. Second application of the circular motion is wheel of death. Okay, so in the wheel of death, rider performs the circular motion on this wall. So in order to maintain its equilibrium, the normal reaction which is offered by the wall, it is equal to the mr omega square, that is the centrifugal force. Okay, so you can see here, this is the force mr omega square, okay, which is equal to mv square upon r. And second equation is its weight, that is the self weight of the rider along with the bike, mg, it is balanced by the static friction. Okay, so mg is equal to fs. Now here the static friction, this is equal to mu s into n. Okay, and condition is for the equilibrium, the static friction, it must be greater than the mg. Okay, so if fs is greater than or equal to mg, then and only then rider will maintain its equilibrium, otherwise it will fall down. Okay, so fs is nothing but mu s into n, it must be greater than or equal to mg, and n from this equation, it is a mv square upon r. Okay, so this is the n, which is a mr omega square or mv square upon r, it is greater than mg, and we get the equation finally, which is the minimum velocity, this is equal to square root rg upon mu s. Okay, so this is the minimum velocity for that rider, so that he can maintain the equilibrium on this wheel of death. Okay, next is the vehicle on the bank road. So here the vehicle is shown, which is moving on the bank road, and this angle of banking is theta for that track. This is the weight mg acting in the downward direction. This is the center of gravity, and this is the normal reaction which is offered by the road surface. Okay, so this is the exactly perpendicular normal reaction. Now as this angle is theta, so normal reaction angle with the vertical, it will be theta. So this component is n cos theta, and this component will be n sin theta. Okay, so here we are interested in the shape speed. So this shape speed is without considering the friction. So in this condition, this n cos theta, it is balanced by the self weight mg, and n sin theta, so it is balanced by the centrifugal force. So it is a mr omega square, or this is mv square upon r. So finally we get the equation for a tan theta, which is equal to v square upon rg. So from this we get the angle of banking for the shape speed. This is theta is equal to tan inverse v square upon rg. So this is the equation for the angle of banking, and the shape speed v is equal to, this is square root rg tan theta. Okay, so if the vehicle is moving at this speed, then we can avoid the skidding of the vehicle. Now on the bank road, we can calculate the speed limit. So speed limit means maximum and the minimum speed. So here we have to consider the friction to calculate the speed limit. So the minimum speed, so for the minimum speed, the friction, that is the static friction, it will act in the upward direction. So here at the minimum speed, friction, it will act in the upward direction because there is a possibility that vehicle will slip down the plane at the minimum speed. So friction will try to oppose this slipping in the downward direction or down the plane. So this is the static friction, Fs, acting in the upward direction. Okay. Then remaining forces are, this is n cos theta, this is n sin theta, and this is a mg. Okay. So this static friction we can resolve like this. So this is theta, this is theta. So this is a Fs cos theta, and this component is Fs sin theta. Okay. So at the minimum speed, we have the equation centrifugal force, which is a mv square upon r, plus the Fs cos theta. It is equal to n sin theta. Okay. So this is the equilibrium equation. This is centrifugal force. Then this is Fs cos theta, which is the friction, and n sin theta acting in the negative x direction. Okay. So from this we get the equation centrifugal force, this is equal to n sin theta minus Fs cos theta. And by using the summation Fy, we get mg is equal to Fs sin theta plus n cos theta. Okay. So these are two equilibrium equations for the bank road at the minimum speed. Okay. So if you solve these two equations, you will get the equation for the minimum speed, which is equal to the square root Rg in bracket tan theta minus mu s upon 1 plus mu s into tan theta. So by using this equation, you can calculate the minimum speed on the bank road for the vehicle. Okay. For the maximum speed, the only change is this friction, it will act in the downward direction. So at the maximum speed, this is the direction of the friction. Okay. So for the maximum speed, I will just write the equation for Vmax. Remaining equations are similar to this equation. So Vmax is equal to Rg in bracket tan theta plus mu s upon 1 minus mu s tan theta. So equations are quite similar for minimum and the maximum speed. Okay. So tan theta plus mu s, here we have tan theta minus mu s. and it is 1 minus mu s tan theta, and here 1 plus mu s tan theta. So these are the equations that will give the speed limit for the vehicle on the bank road. And last application, we have the conical pendulum. Okay. So in the conical pendulum, this stone or a object is tied to a string. So this string is having the length L. Okay. And it is revolved so that it will form one cone. So this is the apex for the cone. So this is the point O. And this is the angle theta. So at the equilibrium, this is the tension in the string, which is a T0. Okay. This angle will be same. It is a theta. So this is T0 cos theta, and this is T0 sin theta. And this is the self weight of this object mg. Okay. So balancing forces are T0 sin theta. This force, it is balanced by the centrifugal force. So this is mr omega square, or this is equal to mv square upon r. And T0 cos theta, it is balanced by the self weight mg. Okay. So if you solve these two equations, you will get the equation for angular velocity omega, which is equal to g sin theta upon r cos theta. Okay. So by using this equation, you can find out the necessary angular velocity. And if r is equal to, so r means the radius of this circle. So this is the r and this is the L. So r is equal to L cos theta, sorry, L sin theta. Then this angular velocity equation, this is equal to square root g upon L cos theta. And the time period equation, this is omega is equal to, that is angular velocity is equal to 2 pi upon t, or this is equal to 2 pi into n. Okay. So omega you can write as, sorry, this t you can write as 2 pi in the square root L cos theta upon g. Okay, so these are the equations for the conical pendulum. This is for time period. This is the angular velocity. So for angular velocity, we have two equations. One is a g sin theta upon r cos theta. And if we replace r by L sin theta, then omega is equal to square root g upon L cos theta. And these are the balancing equations. T0 sin theta, that is the x component of tension, it is balanced by the centrifugal force, and y component of tension is balanced by the self weight mg. Next, we have the vertical circular motion. So in the vertical circular motion, the mass is tied to a string, and if you want to maintain the circular motion, what are the minimum velocities at the various points? Okay. So the uppermost point, that is the point A. So this is the uppermost point. At this point, the mg, that is the balancing equation, is mg plus tension, that is a Ta. This is equal to the centrifugal force. So mva square upon r. Okay. So from this we get the minimum velocity. So v minimum at point A, this is equal to square root rg. Okay. For the minimum velocity, this tension, it will be 0. Okay, and from this you will get the equation as V minimum at the point A is equal to square root RG. So if you maintain this velocity at the point A, then we can complete the circular motion. At the lowermost point, that is at point B, so its equation is tension at point B minus the mg. So here tension and the weight force, they are exactly opposite. So tension is directed toward the center and mg is acting in the downward direction. So T minus mg, this is equal to m Vb square upon R. So this is the centrifugal force. Okay. And second equation to calculate the velocity at point B is we have to use the potential energy and the kinetic energy. Okay. So potential energy at point A, this is equal to the change in kinetic energy from point A to B. Okay. So its equation is, so this is mg to R. This is the total potential energy at this point. Okay. With respect to the point B, this is equal to 1 by 2 m Vb square. This is the total kinetic energy at point B minus 1 by 2 m Va square. Okay. From this, you will get Vb square minus Va square is equal to 4 Rg. So difference in the velocity at point B and A. So this I will write here. Vb square minus Va square. This is equal to 4 Rg. And the minimum velocity, so Vb minimum, this is equal to square root 5 Rg. Just put the value of Va, which is square root Rg, in this equation. You will get the Vb minimum, which is square root 5 Rg. Okay. And the tension difference between. So if there is a question to find out the tension difference at point B and at point A, so that equation is Tb minus Ta. This is equal to 6 mg. So you have to remember all these equations. Tension difference from uppermost point to the lowermost point is a 6 mg. Velocity at lowermost point is square root 5 Rg. At the uppermost point is square root Rg. And at the horizontal point, so we have two horizontal points, C and D. So here we have the minimum velocity, which is a Vc or the Vd. This is equal to square root 3 Rg. And the tension difference from C and A, this is equal to 3 mg. Okay. So this is all about the vertical circular motion. Okay. So you should remember this equation. Minimum velocity at point A, that is the uppermost point. Minimum velocity at point B, lowermost point. Minimum velocity, at the horizontal point, Vc and Vd. Next point is the moment of inertia. Okay. So moment of inertia, its a general formula is I is equal to, it is a summation mi Ri square, where I goes to 1 to n. Okay. Or in the integration, we can write I is equal to integration R square dm. Okay. So suppose we have these masses m1, m2, m3, and if you want to find out the moment of inertia about this axis of rotation, okay, so we can get this value as I is equal to m1 r1 square plus m2 r2 square plus m3 r3 square. Okay. In the moment of inertia, we have two theorems. One is a parallel axis theorem. Okay, so parallel axis theorem means what? Suppose this is one rigid object and this is the center of gravity of that object. Okay, and this is the axis which is passing through the center of gravity, and moment of inertia of this object about the center of gravity, it is a ig. If we are interested in the moment of inertia at any other point, let us take the point O. So this is the axis which is passing through the O, and suppose this object is revolving about the point O, and if you want to find out the moment of inertia, that is the IO, then by using parallel axis we can find out this. So we should measure the distance between these two axes or two parallel axes. So let us take this distance as a h. Okay, and mass of the rigid object, this is the m. Then parallel axis is, that is IO, this is equal to IG, moment of inertia about the center of gravity, plus mass of the object into square of the distance between the two parallel axes. So it is a mh square. I0 is equal to Ig plus mh square. In this case, we must know the centroidal moment of inertia, that is the Ig, and the mass of the object and distance between the two parallel axes. Next, perpendicular axis theorem. Okay, so by using this theorem, we can find out the moment of inertia about three mutually perpendicular axes. So this is one rigid object. Let us take this axis as a ix, this is a y, and this is the z axis. Okay, so these are three mutually perpendicular axes. X and y axis, they lies in the plane of the rigid object, and z is the perpendicular to the plane. Okay, so if ix is known and iy is known, if these two moment of inertia are known, we can find out the remaining moment of inertia about the perpendicular axis, which is the iz. So this is given by iz, this is equal to ix plus iy. So this is the perpendicular axis theorem. Okay, so you have to use these theorems when you will solve the problems. So these are some standard formulae for moment of inertia for the standard geometrical shapes. So first is the thin ring or a hollow cylinder. About the central axis, that is the axis passing through the center, its moment of inertia is I is equal to mr square. Okay, so this is the Ig. For the same object, that is a thin ring, if the axis is passing through the diameter like this, okay, and if the object is revolving about this diameter, then its moment of inertia is mr square upon 2. Then second object is annular ring or thick walled hollow cylinder. Okay, so suppose we take the hollow cylinder and its inner radius is r1 and outer radius is r2. Okay, then its moment of inertia about this central axis is 1 by 2 m in bracket r2 square plus r1 square. For uniform disk or the solid cylinder, central moment of inertia is mr square by 2. So this is 1 by 2 mr square. Okay, and for the uniform disk about the diameter like this, moment of inertia is mr square by 4. Okay, you can calculate this moment of inertia by using the parallel axis theorem. Then next, for thin walled hollow sphere, For the holosphere, central moment of inertia is 2 by 3 mr square. For solid sphere, central moment of inertia is 2 by 5 mr square. Then for uniform symmetric spherical shell, okay, spherical shell means inner radius is r1 and outer radius is r2. This is the formula for moment of inertia, 2 by 5 m in bracket r2 raised to 5 minus r1 raised to 5 upon r2 cube minus r1 cube. Okay. For thin uniform rod or the rectangular plane, about its center of gravity, its moment of inertia is ml square by 12. So this formula is valid for uniform rod and the rectangular plate. For thin uniform rod or rectangular plate, the moment of inertia about a point, which is the end point, one of the end point of that rod, moment of inertia is mr square by 3. This moment of inertia you can find out by using parallel axis theorem. Okay. For that, you should know this moment of inertia, which is a ml square by 12 and distance between the two parallel axes. So right now it is a L by 2. Okay. So by using parallel axis theorem, you will get finally this equation mr square by 3. So this is not r, this is a ml square by 3. And for the uniform plate or the rectangular parallel pipe, the central moment of inertia is 1 by 12 m L square plus b square. Okay. So this is the length and this is the breadth. And last point in the rotational dynamic is the angular momentum. Okay. So angular momentum concept is similar to the linear momentum. So consider a box of mass m and it is kept on the horizontal surface. Okay. And if you apply some force F on this object, okay, so this object starts moving with certain velocity. Okay. So it will gain some momentum during its motion because of its mass and velocity, and this momentum is given by P is equal to mass into velocity. So this is called as a linear momentum. Okay. For the angular momentum, we will use the equivalent terms. So in the linear motion or the rectilinear motion, we have mass, which is replaced by the inertia, that is the mass moment of inertia in the rotational motion. Linear velocity, it is replaced by the angular velocity omega, and this momentum P, which is the linear momentum, it is replaced by L, which is the angular momentum. So L is equal to I into omega. So this is the formula for the angular momentum. Okay. So these are all basic concepts that you should know to solve the objective questions. Okay, so now let us solve the objective question. So you can note it down or you can take the screenshot. Okay, refer the first question. So this is on the kinematics for the circular motion. So in the kinematics, we have to use the formula for linear velocity, angular acceleration, centripetal acceleration, and the kinematic equations. Okay, that is a v is equal to u plus at, s is equal to ut plus half at square. So the first problem is, if 2 pi radian is equal to 360 degree, okay, then 100 radian per second is equal to, okay, so we have to find out the correct answer.
for 100 radian per second, okay, in terms of RPS, okay. So here 2 pi, this is equal to 360 degree, okay. So what is 100 radian per second equal to how many RPS? This is the question, okay. So we know the angular velocity omega, it can be given by this formula 2 pi upon capital T, that is the time period, and second formula is this 1 upon T is nothing but the frequency, so it is a 2 pi n, okay. So n is equal to, this is omega upon 2 pi, okay. So this is equal to, so omega is given as a 100 radian per second upon 2 pi, okay. So this is equal to, this is 50 upon pi, so 50 upon pi, so this is 50 upon 3.40, okay. And if you divide this, you will approximately get the answer as a 16. So this is 16 RPS, or this is 16 Hertz, okay. So sometimes RPS is represented as a Hertz. So finally it is the frequency. So correct option is option C, okay. So to solve this problem, actually this data is not required, because we know 2 pi radian is nothing but 360 degree only, okay. Just you should know this formula, omega is equal to 2 pi n, or omega is equal to 2 pi upon T. Okay, now refer the second question. In half period of revolution, displacement and the distance covered is, the first option is 2r into pi r, second is a pi r 2r, third is 2 pi r 2r, and last is 0 and 2 pi r, okay. So we have to find out in half period of revolution what is the displacement and the distance covered. So half period of revolution means particle will travel the half distance in the circular motion, okay. So it will complete the semicircle. So suppose this is the particle and it is performing the circular motion. So this is the circular motion. Okay. For one complete period of revolution, so particle will perform complete circle. Okay. So one revolution, in half revolution, so particle will travel just a semicircle. Okay. So suppose this is the initial position. So this is the x0 and this is the x1. Okay. And this is the radius r. So displacement and the distance covered. So distance covered means what? Actual path traveled. So this is nothing but the distance. So this path traveled is nothing but the half of the perimeter. So half perimeter is nothing but pi r. So this is the distance. Okay. And the displacement is nothing but the final position minus initial position. So distance is nothing but the actual path traveled or the length of path, and the displacement is nothing but the difference between the final and the initial position. Okay, so here we have the x1 as the final position, x0 as the initial position. So this is the x1 minus x0. Okay, so if you take x0 as a starting point, then with respect to x0, the position x1 is at 2r distance. Okay, so this difference will be 2r. So now select the correct option. Displacement is 2r and distance is pi r. So 2r and pi r. So correct option is option A. Okay. So to solve this problem, you should know the concept of distance, displacement. Okay. Now refer the next problem. So this is the theoretical problem. A particle is acted upon by a force of constant magnitude, which is always perpendicular to the velocity of the particle. The motion takes place in the plane. It follows that its velocity is constant. Second, its acceleration is constant. Its motion is linear, and its motion is a circular. Okay. So actually, this is the problem for circular motion. So what is given? A particle is acted upon by a force of constant magnitude, which is always perpendicular to the velocity of the particle. Okay. So force is perpendicular to the velocity. The motion takes place in a plane. It follows its velocity is constant. So we cannot predict directly whether its velocity is constant based on the force. Okay. Its acceleration is constant, as we cannot say about velocity. So we cannot say about the acceleration. Its motion is linear. Motion cannot be linear if the force is perpendicular to the velocity. Okay. So only possible option is its motion is a circular. Okay. So when force is a perpendicular to the velocity, then it will perform the circular motion. So correct option is option D. Okay, now refer the fifth question. If a particle moves in a circle describing equal angle in equal time, particle moves in a circle describing equal angles in equal time in a plane about a fixed point, its velocity vector remains constant. Second, changes in magnitude, changes in direction, changes both in magnitude and direction. Okay. So what is given? If particle moves in a circle describing, so this is the circular motion. This is the particle P. Okay. And this is the tangential velocity. This is the successive position. So this is the P1, this is P2, so on. Okay. Equal angle in equal time in a plane about a fixed point. Suppose this is the angle theta. It takes the time t. Okay. Then its velocity vector, it remain constant. So velocity vector cannot remain constant, because even if the velocity magnitude is constant, still its direction will change. So you can see here the change in direction. Okay, so first option is wrong. Velocity vector remains constant, vector cannot remain constant. Second is changes in magnitude. Velocity vector, if it changes in magnitude, its direction will also change. So this is the wrong option. changes in direction. Okay, so vector, it will change the direction. So this is the correct option. Last option is changes both in magnitude and direction. Okay, magnitude will remain constant because here equal angle in equal time, that means omega is constant. Okay, as omega is constant, mod v, it will be constant because v is equal to r omega. Okay, but vector v bar, it will change. Okay, so it will change only in direction, not in magnitude. So D is wrong. So correct option is, if particle describes equal angle in equal time, then velocity vector, it will only change the direction. Okay, not the magnitude. Magnitude will remain same. The next is direction of angular velocity in uniform circular motion is first along the tangent, along the radius, along the axis, and along the chord. Okay, so angular velocity, so this is the circular motion, and suppose this is the point P, it performs the circular motion in this direction. So direction is given by the right hand thumb rule. So you should curl the finger like this, then this thumb, it will denote the direction of the angular velocity vector. So this is the axis which is perpendicular to the plane of circular motion. This is the direction for velocity vector, that is the omega bar. Okay, so direction of angular velocity in a uniform circular motion is along the axis or the parallel to the axis. So correct option is C. Okay, along tangent is the linear velocity, not the angular velocity. So this is the linear velocity vector v bar. Okay, so here direction of angular velocity in uniform circular motion is along the axis. If this is angular acceleration, answer will remain same, along the axis. Okay, refer the next question. So I think this is sixth, and this is the seventh question. Okay, just read the problem and think about the solution. So what is given? The angular velocity of a wheel is 70 radian per second. If the radius of the wheel is 0.5 meter, then its linear velocity will be. Okay, so this is simple question which is based on the equation v is equal to r omega. Angular velocity of the wheel omega, this is equal to 70 rad per second, and the radius of the wheel, which is equal to 0.5. Okay, then the linear velocity v, this is equal to, so we have the equation v is equal to r into omega, that is the linear velocity is equal to radius into angular velocity. So here r is 0.5 into 70. Okay, so this is 35 meter per second. Okay, so option is option C. So you should know this formula to solve the problem. You can take the screenshot directly. Now refer this question. angle between the radius vector and the centripetal acceleration is, first is pi by 2, second 2 pi, third 3 pi by 2, and fourth is the pi. Okay. So in the circular motion, so this is the center point, and this is the particle which is moving on this circular path. This is the linear velocity v bar. Okay. Then this is the radius vector. Okay. So this is the r bar, and the centripetal acceleration. The meaning of centripetal acceleration is the acceleration is directed towards the center. So this is centripetal acceleration. Okay. So we have one vector, which is the radius vector r bar, and this is the centripetal acceleration vector, which is the a bar. So this angle, this is pi angle. Okay. So angle between radius vector and the centripetal acceleration vector is, the correct option is option D. Okay. Angle is pi. Okay. Now refer this problem. A particle moves in a circle of radius 25 centimeter at 2 revolutions per second. The acceleration of the particle in meter per second square is, okay. So what is given? Particle is performing the circular motion. Its radius is 25. So this is 25 centimeter. This is the linear speed v, and its speed is given as a 2 revolutions per second. So 2 revolutions per second. So you refer this revolutions per second. So revolution per second RPS is nothing but the frequency. So it is a n, and it is given as 2 revolutions per second. So n value is given. Okay. What else is given? Radius is given for that circular motion. So r is equal to 25 centimeter. And what is the question? Acceleration. So we have to find out the acceleration of the particle. Okay. So we have the formula for acceleration, which is a is equal to r into omega square. Okay. And omega, it's 2 pi upon t, or this is equal to 2 pi into n. Okay. So you can put this value of omega in this equation, which is a 2 pi n. So acceleration is equal to r into, this is 2 pi n square. So this is equal to r 4 pi square into n square. Okay. Now r is given. So r is equal to 25 centimeter. So this is equal to 0.25. Okay. So you can put this here, 0.25 into 4 pi square into n square. Okay. So n value, this is given as a 2. So n square will be 4. So this will be 16. So this is 16 into 0.25 pi square. Now 0.25 is 1 by 4. So this is 1 by 4 into 16. So this is 4 pi square. Okay. So your correct option is option C. Okay. So you should know this formula of RPS means small n. Then omega is equal to 2 pi upon t or 2 pi into n. And acceleration is equal to r omega square. Okay. Correct option is 4 pi square, option C. Okay, now refer this problem. The work done by the centripetal force F when a body completes one revolution around a circle of radius r. Okay, so centripetal work done by the centripetal force, it is always 0, because in the circular motion force acts along the radius towards the center, and particle's velocity is perpendicular. Okay, so there is no displacement of the particle in the direction of the centripetal force, and therefore work done, it is 0. So work done in a circular motion is always 0. So correct option is option D. Okay, now refer this next problem. A cyclist turns around a curve at 40 km per hour. So this is the speed. If he rounds the curve at double speed, his tendency to overturn. Okay, so we have to find out it's a velocity. So velocity v, this is given by, so it is given in the problem as a 40 kilometer per hour. Okay, so convert this velocity in meter per second. So conversion is just multiply it by 5 by 18. So this will be 100 upon 9. So this is meter per second. So if the rider is moving at this speed, and if he rounds the curve at double speed, so if the speed is increased, let us take this as a v1. v2, this is equal to 2 into v1. So the tendency of overturn, it depends on the centrifugal force. So centrifugal force is equal to, initial force is F1, which is equal to m v square upon r, and when the speed is doubled, its centrifugal force is m v2 square upon r. So here v2, this value is equal to 2v1. So this is equal to 4 m v1 square upon r. So this value is nothing but the initial centrifugal force, which is the F1. So F2 is equal to 4 times F1. Okay, so when the speed is doubled, centrifugal force becomes 4 times that of the initial force, and therefore his tendency to overturn, correct option is quadrupled. Okay, it means 4 times. So correct option is option D. Okay, now next point is vehicle on the circular track and the banking of the road. Okay. Now refer the first problem. A cyclist moves in a circular track of radius 50 meter. If the coefficient of friction is 0.4, then maximum velocity with which cyclist takes a turn without leaning inward is. So the maximum velocity for the cyclist we can find out by using this formula. V is equal to square root mu rg. So mu is given, which is the coefficient of static friction, which is the 0.4. Then radius of the track is 50 meter and g is 9.8. So if you solve this, you will get the answer as 14 meter per second. Okay, so the option is option A. Refer this second problem. A circular road of radius 1000 meter has a banking angle of 45 degree. Its maximum speed so that a car with mass 2000 kg will not skid, and coefficient of friction between tire and the road is 0.5 meter. Okay. So here the angle of banking is given as a 45 degree. And this is the vehicle. Its mass is 2000 kg. We have to find out the maximum speed. Okay. For the maximum speed, we have the equation Vmax. This is equal to square root Rg in bracket tan theta plus mu s upon 1 minus mu s tan theta. Okay. Now theta is given as a 45 degree. So tan 45, that is a tan theta, this is equal to 1. Okay. And mu s, coefficient of static friction. So this is a 0.5. So put these values in this equation. R is 1000. So this is 1000 into 9.81. In bracket, tan theta is 1, that is a tan 45 plus 0.5 upon 1 minus 0.5. Okay, so this is equal to, so this is 1.5 upon 0.5. Okay, so you can simplify this equation. So once you simplify this equation, you will get the equation as this is square root 3 into 100, and this is 1.73. So your answer is 173 or 172. So your correct option is option D. Okay. So the basic formula that you should know is maximum velocity for a vehicle moving on the bank circular road. Okay, now this is the problem on the vertical circular motion. So in a vertical circle of radius r, at what point in its path particle has a minimum velocity? Okay, so particle has minimum velocity. So v minimum in a circular motion is square root rg, and this velocity
It is at the highest point. So correct option is option A. For the second problem, a can filled with the water. It is revolved in a vertical circle of radius 9 meter. The water does not fall. The time period of the revolution will be. Okay. So as the water does not fall, it means the weight of the water, it must be balanced by the centrifugal force. So this is the vertical circular motion. Okay, so the weight of this water, it will act in the downward direction, and centrifugal force acting on the all water droplets or particles, it will act away from the center. So this is a mr omega square. Okay, so for the equilibrium, as water does not fall, weight of the water mg, it is equal to mr omega square. Okay, so from this, g is equal to r into omega square. Okay, so what is given in the problem? The radius is given. So r is given as a 9 meter, and question is we have to find out the time period of the revolution. Okay, so we need to write this omega in terms of time period. So we have the equation for omega. So omega is equal to 2 pi upon t. Okay, so put this equation. So g is equal to r in bracket 2 pi upon t bracket square. So this is equal to r 4 pi square upon t square. Okay, and just write this equation for the t. So this is equal to t square is equal to, so this is 4 pi square into r upon g. Okay, and r is given, this is equal to 9 meter. So this is 36 pi square upon g. Okay, and g we can approximate as a pi square. Okay, so finally you will get the answer. T square is 36, so t is 6. Okay, so you should remember this approximation. The acceleration due to gravity g, this is approximately equal to pi square. So correct option is option C. Okay, so to solve this problem, you should know this equilibrium equation. Weight is equal to the centrifugal force, and this formula for omega 2 pi upon t. Okay, so we will solve this last problem and then we will stop. So this is on the moment of inertia. So if I1 and I2 are the moment of inertias of two bodies of identical geometrical shapes, then the first is of aluminum and the second is of the iron. So we have to find out the relation whether I1 is less than I2, I1 is greater than I2, I1 equal to I2, or I1 is greater than or equal to I2. Okay, so aluminum density is less than the iron. Okay, so density of aluminum is less than density of the iron. So as density is less than density of iron, so mass of the aluminum for the same geometrical shape and the size, it will be less than mass of the iron. Okay, and as mass is less than mass of the iron, that means its moment of inertia I1 is less than moment of inertia of the ion. Okay, so moment of inertia of aluminum, that is I1, is less than moment of inertia of the ion. Okay, so correct option is option A. Okay, you can note down the next problem and you can try this as a homework. So remaining problem we will solve in the next lecture. Okay.